Hello, this is Christian Idealism, and today we're going to be looking at the science behind philosophy of time. This is, of course, brought to you by Cal Allender with a contribution by Johanan and Raatz. And so we need to ask the question, is space-time absolute or relative? Well, there are many problems with space-time being absolute. So first, let's consider a philosophical thought experiment. Now, keep in mind, Johanan Raatz will go over this thought experiment again, but for now, let's actually present the thought experiment. So, here it goes like this. Imagine a completely empty space as thought of by the ancient Greeks, which is atoms in the void, you have no relativistic space, and this empty space is infinite. Since space is what defines the distance between 2 points, try and imagine the center of this infinite space. Now, since we have nothing to reference it to, other than the endpoint of this space, which would be going to infinity, we measure infinity from both sides of the center point. Now, imagine we put another point in between the center point and the endpoint of the infinite space. The problem, of course, is that half of infinity is still infinity, and so this center point would therefore be both at one point and it would be infinitely far away from the second point. But since this center point, or this absolute reference frame, is supposed to define all other points in this absolute space, this infinite space, or this infinite void for that matter, is not actually absolute space, since it would actually create a lot of contradictions. And so what makes it space is its relativistic nature. To create space means to create particle location, since you cannot have empty space without points of reference. Otherwise it becomes internally contradictory. And so space-time is nothing more than a network of relationships of points, and likewise these points come out of the wave function. In quantum mechanics, a particle's location is not fixed until it's collapsed. And since location is not defined by location, then these points which makes up space depend on the wave function, which is relativistic in nature. And so, therefore, we know that both philosophically and scientifically, that space-time must be relative and cannot be absolute. And so, let's go into special relativity here. So, special relativity follows from two fundamental assumptions. So the first assumption is that the laws of physics are the same in all reference frames, and then the second assumption is that the speed of light is the same in all reference frames. These two assumptions explain all of the scientific data regarding special relativity. There is no need to add anything more to this theory. Since we established before why space-time cannot be absolute, then under special relativity, all reference frames are just a network of relationships in which time is relative to each observer and doesn't depend on any absolute reference frame. We know that time dilation and length contraction happen because we have seen many examples of them. A perfect example of this would be muons. Under classical physics, even if muons were moving at 99.999999% the speed of light, that is not enough for them to reach the ground, where particle detectors would find them, because they would decay before they're even 1/10 to the bottom of the ground. However, under special relativity, time dilation and length contraction make this process possible, and can be shown that from the reference frame of an observer from Earth, that time is slowing down for the particle, which allows it to last long enough to hit the ground and be detected. However, from the reference frame of the particle, it is not slowing down, but its distance is shorter due to length contraction, so it hits the ground before decay. And so, if this process never occurred, then particles could never reach from the upper atmosphere down to the ground, since they would decay much quicker and they wouldn't be able to reach the ground. Yet we detect them doing exactly this, and so that would be kind of the confirmation of time dilation and length contraction. And so what are the implications of this? Well, the implication is that if space-time is relative and if time dilation and length contraction occur in our universe, then when applying this to the universe as a whole, there is no absolute time from which the universe goes through. Instead, time is relative to each reference frame and works differently throughout the universe. This means that if I looked out into the universe, I could in fact be seeing the past, and likewise, from an alien's point of view, they would be looking at my present and so on and so forth. And also I want to point out that if a frame starts to move away from another frame, then the difference between the time actually increases. And so the way that physicists have modeled the universe in this way is called the block time model, where we are in a four-dimensional block universe. This is used to explain how to keep the universe in an observer independent, in the sense that while it's true that no absolute reference frame exists, it's false to say that space-time doesn't strictly depend on observers, since the universe would be truly four-dimensional in order to hold on to the belief of an observer-independent reality. So while it's true that time is different for observers, the universe does not depend on observers, and so this is kind of the reason why a lot of physicists hold this view. Well, let's go over the assumption behind the observer-independent reality. So to address the idea of observer-independent reality, we need to look no further than quantum mechanics and quantum gravity and its explanation of emergent spacetime. An observer-independent reality only works if there is some mechanism other than observers that can explain the emergence of spacetime. However, these attempts fail, which is why physicists are now using what's called observer-dependent cosmology to explain spacetime. And so, I will close this video by having Johanan Raatz explain the absurdity of absolute spacetime and explain emergent spacetime and why it cannot allow an observer-independent reality. He's going to repeat some of the same points I mentioned before. However, he will give us insight into how spacetime emerges from quantum mechanics. And so, now, the rest of the video goes to Johanan.
To start out with, try to imagine a completely empty space as thought of by the ancient Greeks, right? Just atoms in the void, nothing unusual, no relativistic space, but even no quantum fluctuations. Pretend we don't even know about quantum mechanics. We're going to imagine a completely stark, empty void as we intuitively think of it. Now, keeping in mind that space is what defines the distance between or the difference between 2 points, try and find the center point of this infinitely empty void. We have nothing to reference it to other than the endpoints of this empty space going from infinity. So naively, we measure off infinity from both sides and we find the center point. But there's a problem with this. Half of infinity is also infinity, right? So this center point is simultaneously at one point and infinitely far away from itself. And well, if you think about that, that's a contradiction in terms. But the center point defines all other points in this empty space, and so because of that we can actually see that this notion of empty space that we intuit, it falls apart on close inspection. This infinitely empty void is not actually space. To think of it as space generates contradictions. Now let's add in a single particle and see what happens. So where in this infinitely empty void is this particle exactly? Well, this particle has nothing to reference itself to other than the edges of this infinitely empty void, infinitely far away. And so as you can see, it falls right into the same problem as before when we had a simple empty space and we were trying to find where the center point of the space was. So the curious conclusion from all of this is that this particle isn't actually existing in space. But now we have a second problem. Particles by definition have spatial extension. And so, well, since this isn't in space, it doesn't have spatial extension. So this becomes a mighty peculiar particle here. It's a particle, but it doesn't behave like a particle. It doesn't have spatial extension. It can't interact with anything because there's nothing around to interact with, and so there's no timeline of events it's on either. A timeline of events would have to be measured off from both an infinite future and an infinite past, and so we'd have the same kind of problem as we would for infinite space. And as a result, this so-called particle doesn't actually even have any physical units at all, because you need to have space and time to have matter or energy. So what is this particle? Well, you've stripped away all of the physical units, and the only thing left to call this particle is not a particle at all, but a bit of information. So when you see it like this whole notion of the universe being made of information, it's not really so surreal anymore, it's actually fairly intuitive. Now remember, information always increases with time, and there's a finite amount of information in the universe, and so you go back at some point, and this picture I just described, it wasn't just a hypothetical scenario. The universe actually was in this at the beginning of time. Now what's the entropy of the universe at this point? Well, there's only one microstate in the universe, and the natural log of one microstate is 0. So the entropy is also 0. And of course this perfectly accords with the holographic principle, where, well, you have 0 entropy equals 0 spacetime, and that makes sense because this bit of information is not defined in space or time. In order to bring space into this, you have to have another bit of information with which to relate the second bit of information. And once you have that, well, you can have 2 microstates. You can have either the first bit of information going first, the second bit of information going second, or vice versa. And now you have two possible arrangements of these, two microstates or channels of information, as Lee Smolin would put it. And once again, this accords with the holographic principle, because you take the natural log of two microstates and you get a finite number, which corresponds to a finite amount of space. So what does this all have to do with space and time not existing at the quantum scale, or at least not insofar as quantum gravity is concerned? Well, as I demonstrated before, these particles have to have fixed locations before they can relate to each other and create space. Without locations, you can't define what space is. And of course, this comes to a whole chicken or the egg paradox. What came first, the locations or the space? Because obviously locality is defined in terms of space. Well, the answer is that they both came out at once. Space is nothing more than a network of relationships, of points. And these networks of points come out of the wave function. Remember, in quantum mechanics, a particle's location is not fixed before you collapse its wave function. And because location is not defined before you collapse the wave function, space isn't defined before you collapse the wave function either. And, well, the same argument holds for time, because you can treat events as equivalent to locations. And you can actually see some evidence of this in standard quantum mechanics. This is, forgetting quantum gravity for a second, you can actually see evidence of space breaking down in, for example, quantum entanglement. You have two particles that share the same wave function, and one of them behaves as though it's very close, even though it could be miles away from the first particle. What happens to the one affects the other instantaneously, as though there was no space between them at all. So because of this, your argument kind of falls apart, because, well, there really isn't any space or time at the quantum level in the first place. So to refer to the quantum level like this defeats your own argument.